Alright, that's yeah, there's no real good way to do this lighting. Hey guys, I hope you're doing alright. I know it's a little bit different, but, you know, we're going to make the best of it. So, what I'm going to do is I have my email in the corner of this video. If you have any questions or comments or anything. You can also speed this up, slow down, go back, whatever. So, you know, that's nice for what it is. So more or less things will be exactly the same. I don't know how many of you are actually going to watch this, so I'll try to make it as entertaining for you as possible, because I appreciate you. Thank you for watching this, because I put a lot of effort into that intro. So, the question I'm going to go over with you guys today, from the book, it's problem 9.2. And the problem is about a flow going between two parallel plates. And we have water flowing through here, and we have point A and point B. Distance between point A and point B is going to be 900 millimeters. The thickness between the two plates is going to be 4 millimeters. And the width is going to be 600 millimeters. I also didn't test the audio on this, and I realized that the mic there isn't plugged in. So I'm going to stop this and make sure that the audio looks alright. Okay, that should be much better. I'm not going to redo the first part because I don't get paid enough to do that. Sorry, let's get through the rest of this problem. So, we have our flow between two parallel plates, and we're tasked with finding the flow rate Q, the magnitude of the shear stress on the top plate, and the magnitude of the shear stress on the bottom plate. So, starting with flow rate. Oh wait, sorry, one last important thing I forgot to mention. We're given that the temperature of the water is 20 degrees Celsius, and ooh! Oh, okay. We're told that delta P is equal to, you have the pressure differential between A and B is going to be minus 150 pascals. So given this information, these are all our givens, we need to find those three values. So starting with flow rate, from Appendix A, we can look at the qualities, Hey Lila. properties. The properties of water at 20 degrees Celsius from Appendix A. Density is going to be 998.3 kilograms per cubic meter. And the viscosity is equal to 1 times 10 to the negative 3 Pascal seconds. So from here we have a relation that we can use where we can say that the velocity of the flow is equal to negative t squared, where t is the gap between the two plates, over 12 mu times dp dx. We can say that's equal to that times, since we can assume that P will differ linearly along along the point A to B, we can just say that that's equal to delta P over L, that guy right there. So you work this out, you plug in the numbers, you have your delta P is 150, negative 150 pascals, your L is 0.9 meters, you have your mu, and then T is going to be equal to 0.004 meters. That'll give you a value of 0.222 meters per second. And then you guys probably know what to do from here to find your Q. You're going to multiply your velocity times the base and this gap length. So you have this cross-sectional area. So you have 0.004 meters times 0.6. So plug in those values. 0.6 meters times 0.004 meters, and you get a final flow rate of 5.33 times 10 to the negative 4 meters cubed per second. So nothing too out of the ordinary other than this. I don't know if you guys have used this relation before, but this is the first time that I'd seen it in the progress of this course. But yeah, that's how you apply it in this sort of question. Fun fact, the reason I have a blackboard in my house is because I used to be homeschooled all 12 years. Shout out to all my, the two other homeschoolers at the University of Delaware. So now we're going to look to find the magnitude of the shear stress on the top plate up here, and we're going to use a new relation again to find that. Pretty simple. It's going to be dP over dx times T over 2. And again, we discussed dP over dx if we assume that the pressure differs linearly from A to B. Then we can say that dP over dx is simply going to be equal to delta P over L. Multiply that by T over 2. And again, T is the thickness between these two plates. So you have all your knowns. Plug in the values for that, and you will get that tau sub t is equal to 0.333 pascals. And finding the shear stress on the bottom plate is extremely similar. Actually, the only difference in the equation is that there's a negative sign in the front of it. And that doesn't really matter since all we're doing is finding the magnitude. So we already solved for tau sub t. And again, since we're just finding the magnitude, we can just say that tau sub b is 0.333 pascals. So again, just keep in mind that negative sign out front. Again, get in contact with me if you have any questions. Hope you guys are staying safe, staying healthy, and I'll see you next week.